Hello everyone, my name is Akshay Tamboli and my project partner is Mehta. We are implementing feature extraction as a term project in EE278 under the guidance of Dr. Chang Chu. As we know, feature extraction is a very important concept in image processing. Feature points means corner points which convey important information in images when images are captured in sequence. Now let us come to the algorithm part. We are using feature extraction algorithm where we are taking a grayscale image as an input and also we will take number of feature points as an input. We are taking a Lena image as an input where the size of that image is 128 by 128. We are taking that image as an input in MATLAB. As you can see, the input is this image. We have calculated the feature points of this image in MATLAB and the total number of feature points that we have calculated are 3600. For reading this image, we have used image processing toolbox of MATLAB, and as you can see, here is imread and imshow functions which are used to read and show the image. The output of this image will be a 3x n size matrix. Where the first row will be the degree of confidence value, the second and third row will contain the x and y coordinates respectively. We have to find out the image gradient of each pixel by convolution, and we are taking 3x3 mask for calculating the convolution. After getting the calculation, after calculating the convolution, we will now need to calculate the covariance, which are A, B and C values. And we can calculate the covariance which are A, B and C values using this formula. The feature point values, which is P of ij, is calculated by substituting the values of A, B and C in the given formula of P of ij. For calculating the feature point value, we will need a threshold value, and we are using a threshold value of 55 for this project. If the feature point value is greater than threshold value, which is 55, then we will retain that pixels, and if the feature point value is less than threshold value, we will discard that pixel. Now let us come to quarters. We need to create a new project. Next. Here we need to choose a folder. Which will be a working directory. So the working directory is selected. Now we need to name this project. We'll name this project as feature underscore quarter underscore extraction, and we'll set the top level design entity as feature underscore qsys underscore extraction. Next. We need to select a family. So we'll select the Cyclone 2 family. The pin count will be 484 and the speed grade will be 7. So this is the family we are selecting. Here for simulation we are using model sim and format is Verilog HDL. Next. Finish. Now let us go to QSys. Here we need to add a new component. Let us give that component a name. The display name should also be the same name. And the group as my component. Next. Here we need to add a file. We are going to need the hardware accelerator file. Open. Then we'll analyze and synthesize this file. Zero errors and zero warning. Close. Next. Next. Here we need to assign it to Avalon slave, each and every signal. Then next. Here the associated clock should be assigned to clock. The reset is assigned to none. And here the associated reset should be assigned to reset. Then we are going to remove all the interfaces with which don't have any signals. Finish. Save yes. Now we'll select the components. First we should select NEOS 2 processor. NEOS 2/E should be selected. Then we'll need on-chip memory. The size of memory should be 16384. Then we'll need a JTAG. Just finish it. Performance counter. Finish. Then a new component. hardware accelerator. Finish. Then we need to assign clocks and reset to each and every components. So the clock should be assigned to NEOS 2 as well as on chip and JTAG, performance counter and hardware accelerator. Same goes with reset. As clock and reset signals are assigned to rest of the components, we also need to assign data master signal. And instruction master should be assigned to on-chip memory only. Then we also need to assign clock in reset. And connect to this interrupt. Then we need to assign base address. As you can see, the base addresses are assigned. The base address is 9000 for hardware accelerator and 9200 for performance counter. Then we need to change reset vector and exception vector. Let's assign it to on-chip memory. Finish. And we are set for generation. So let's generate it. Save yes. Here the file name should be the same as we have given the top level entity. And that name was feature underscore QSys underscore extraction. So let's save it. It will take some time. So no errors. Let's close it. Now let's go to quarters. Add or remove files. Here we need to select a .qip file. This is .qip file and this we are going to select it. We'll need to add this file. Say OK. Let's go to quarters. We need to assign it as a top level entity. Now let's go to assignment editor. Here we need to assign clock. This should be selected as location, and the value is pin underscore L1. This should also be selected as clock underscore clock. Here we need to select IO standard, and the value should be 3.3 volt LVTTL. Let's just save it. And we are good to compile. This is compiling. It will take some time. It's almost done. So no errors. Now let's go to programmer. Here we need to add some file. Output files. Here we need to add a feature underscore qsys underscore extraction.sof file. So let's start it. It's 100% successful. So let's close it. Yes, save it. Save. Now let us go to Neos. We'll select the folder, and that folder should be feature underscore extr underscore software. Okay. Let's create a new BSP template. Here we need to import a .sopc info file. This is a file which is .sopc info file. We need to import this file. Let's give a application project name as quartus underscore feature. And we need to select the project template as hello world small. Next, finish. It will create a C project. So the build is finished. Now let's see the hello world program. This is the by default hello world program. So let's build this. Build project. It will take some time. So the build is finished. Now let's burn this into our Neos 2 hardware. We should expect a hello world from Neos. And we are getting a hello world from Neos. Now let's copy our C code and paste it here. Let's build this project. This is our C code. Here is the hardware accelerator part, and here is the performance counter part. Now let's run this C code in Neos 2 hardware. Here we can see the output, and it took us almost 5,150,708 clock cycles